Okay, so I'm going to put this video. It's interesting. It's a bit long, maybe 20 minutes, but it's a good one. You can see it? You can see it's too bright? It's okay.
My name is Leslie Lamford, and I am a computer scientist, which is something that didn't really exist when I started being a computer scientist, and it took me a while to figure out that I was one. My relationship with computers began as a programmer. It never quite occurred to me that I was doing anything scientific until after I had published enough papers that it finally occurred to me. My education was as a mathematician. It was just natural for me to think about computers as a mathematician. When you write an algorithm, you need to have a proof that it's correct. An algorithm without a proof is a conjecture. It's not a theorem. And if you're proving things, well, that means mathematics. Computer scientists tend to think in terms of programming languages. One of the epiphanies in my career was the realization that I was not writing programs as a computer scientist, I was designing algorithms. I came to realize that if I'm not writing a program, I shouldn't use a programming language. People confuse programming with coding. Coding is to programming what typing is to writing. Writing is something that involves mental effort. You're thinking about what you're going to say. The words have some importance, but in some sense that even they are secondary to the ideas. In the same way, programs are built on ideas. They have to do something. And what they're supposed to do, is like what writing is supposed to convey. If people are trying to learn programming by being taught to code, well, they're being taught writing by being taught how to type. And that doesn't make much sense. The best way I have for teaching about programming, as distinct from coding, is to think about what the program is supposed to do mathematically. There's a very big practical problem with this. The mathematical education in this country is pretty terrible. Most people wind up being afraid of mathematics. This is even senior programmers. I've developed a language called TLA Plus for writing down the ideas that go into the program before you do any coding. It's a pretty hard thing for engineers to get into, but when they do, it develops their ability to think mathematically. Distributed system is one in which your computer can be rendered useless by the failure of a computer that you didn't even know existed. Non-distributed computing is when different processes communicate by using the same memory. And distributed computing means that they're communicating with one another by sending messages. Now, my interest in distributed systems came about by serendipity. I received a preprint of a paper by Robert Thomas and Paul Johnson, who had an algorithm for implementing distributed databases. These are databases where you could have multiple copies of the data sitting in different computers, so that programs on each computer could have rapid access to the data. But they had to be synchronized so that processes on all computers got consistent views of what the data was. I happen to have become quite familiar with special relativity. One of the things that special relativity teaches you is that two different observers have different notions of what at the same time means. But there's one notion that is invariant. There's a certain notion of one event happening before another event. And that means that it's possible for information to be transmitted from one event to the other when the information cannot travel faster than the speed of light. I realized that that notion of causality was violated by the algorithm of Thomas and Johnson. It's completely analogous to the relation of special relativity. So what I did is I wrote a paper that explained this notion of causality. One could solve any distributed system problem by building what I call a state machine. Think of it as abstract computer that does one thing at a time. To make sure that all the computers in this distributed system cooperate to implement a single state machine. And that idea has become fundamental in the way people think about building distributed systems. I had never even thought about a distributed system before I wrote that paper. As I progressed in my career, I came to appreciate the idea of working in industry. That's where most of the interesting problems that I found came from. From engineers having a problem to solve. It reminds me actually of something that Auguste Renoir said when someone asked him why he painted outside rather than in the studio. And what he said is, if I were painting in the studio and I wanted to paint a leaf, I would be able to think of only a half dozen or so different kinds of leaves I. But when I was painting outdoors, there were just these millions of different kinds of leaves that were there that I could paint from. I found my research the same way, that if I sat down, and just contemplated my neighborhood and thinking about problems, there's a small number of problems that I could think. But there were just scads of them sitting out in industry waiting to be solved. My favorite of my algorithms is the bakery algorithm. It's to solve the mutual exclusion problem, that is, keep two processes from using the printer at the same time. Process is to choose a number based on the numbers that have been chosen by other processes and use an algorithm so that the lowest use the printer. Well, what is amazing about it is it does not make an assumption that almost every other algorithm makes. The assumption being that if, say, I'm changing my number from 47 to 100, and you read that number, you'll either get 47 or 100. But that algorithm works, even if instead of getting 47 or 100, maybe you got 4,700, or maybe you got 9,999. The algorithm still works. I didn't intend it to, I didn't intend it. I just discovered that when I wrote the proof, I never needed to make the assumption. That is just so beautiful. And, I'm really proud that I stumbled on it.
Okay, so this is a necessary reflection when we saw the derivation of how Google was created. We saw this morning how Google was created. So it's, I'm going to talk about another business case now. It's the case of Scotiabank. This is, as I mentioned in the morning, this is the story in which a bank buys a supermarket. I will briefly mention at some point the story which is the reverse, which is a supermarket creating a bank. Didn't buy a bank, they created a bank. And this is a story that goes back to, I forgot what year, but maybe 15 years ago. That's my guess, 15 years ago, maybe 2010, something like that. And this Canadian bank had a deal with a supermarket in Chile. Scotiabank is, just to give you some background, is a bank. We have 5 major banks in Canada. This is one of the 5. And it's the bank that has a very big operation in Latin America. They have major branches in Mexico, Chile, Colombia, and Peru. And this is a story about their Chilean operations. And I believe this is how they started. I think they're much bigger now, but they started like this. They made a deal with the supermarket. This is a supermarket like the one we discussed earlier this morning, which is supermarket with registered clients. They have a loyalty system or something like that, so they know who their clients are. And Scotiabank got into the micro loan business in the following way. The way the business works is if you're a registered customer, when you go to buy your milk and your strawberries, then you can ask for a loan up to $300 at the counter. Okay, and when you ask for the loan, the following thing happens. Behind the scenes, within 5 seconds, the profile is accessed by Scotiabank in some way. We'll discuss this. It's very interesting. Then this is put through a machine, a type of a neural network or something, that gives the answer to the supermarket. And the answer is either yes or no. 5 seconds, you have to do that. So let's get into how that works. What's in that data? Well, first, we don't know. We can only hypothesize what's in that data. But this is the data that the supermarket collects every time you use those loyalty cards. I don't know. Do you have a loyalty card with any supermarket? You do? Yes. Maybe not with the supermarket, maybe with another retailer, maybe? Okay, yes. Yeah, I do. I have some of these loyalty cards in the ones where I am interested in what they have to offer for some reason, right? I have many loyalty cards with many different companies. And with supermarkets, I only have one, I believe. I have loyalty cards with other corporations, again, if I'm interested in that. But their interest is, of course, in my data, and I know that. And in most cases, I don't care. So as explained to me by the bank, what is in those loyalty cards is the following thing, and this is very interesting. When you buy something, that goes into the database, but with it is your entire customer profile. So typically, they ask for very little information when you sign up. And not only they ask for very little information, they oftentimes don't ask for proof. For example, they may ask you, what's your profession? And you can say, I'm a student, I'm a lawyer, I'm a doctor. They don't ask for proof, they just believe you. Okay, that goes into the database. But then they have your shopping habits. Sometimes you also tell them where you live, and they don't check. But because they know your shopping habits, they know where you buy, they probably have a pretty good idea where you actually live and where you actually work. And typically they will also know, without you telling them, how much money you make, because they see what you buy. People with high income buy things different from people with low income. Now, this is a very interesting, this is not in my discussion here, but it's a very well-known case. No, hello, we're happy to see you. Happy to see you. There's a very well-known case related to this notion of guessing and knowing about your customer, which is, you may know this, Walmart. You know the case of Walmart. So Walmart began, it was around the same time, a long time, 2010 or so. There was the following situation. A man lived with his daughter at home, and I think the mother was not there. I think it was just the two of them. The daughter was probably 16 years old. Okay, so the father was, who knows, 40 or something. And one day, the father goes through the mail and sees a brochure, catalog from Walmart directed to his daughter. Then looks at the catalog, and the front page was full of advertising for baby products. Baby products. So the father became very upset and went to Walmart, very upset. In the United States, this can give rise to a lawsuit. And his contention with Walmart was that they were trying to encourage his daughter to become pregnant. That was the reason for his wrath. He was very upset. So the manager of Walmart apologized. He said, "No, sorry, sir, we have no intention of that. This is done by our systems. I really have no idea why this was done." I think there was an attempt of a lawsuit or something, but that's not important. The important thing is that, and this is in the books, this is documented, his daughter was pregnant. He did not know, and Walmart knew. Not for sure, but he had suspicions, to the point that they were trying to sell her baby stuff because Walmart thought that she was going to need it. So this is a very interesting situation, and goes to what we discussed this morning and what we're talking about now and everything. And the reason why you're here, because this program exists because this is the new reality in which data science is changing businesses from within. And finance is typically the way that the changes happen. Okay? So how can a supermarket, a retailer, Walmart, have access to information which is so sensitive just from everyday actions? And that's what machine learning does. That's what neural networks do. That's what modern day algorithms do, if you feed them good data. So apparently, his daughter, went shopping to Walmart, that's number one, probably had a loyalty card or some way for Walmart to identify who she is. And Walmart knows what she bought. Maybe she bought a home pregnancy kit. Maybe Walmart knows exactly how many she bought and exactly when, right? And they know that when you have that pattern, then, well, at some point you become pregnant and you stop buying them, right? The father did not know. So they have access to information which is very, very significant. By the way, retailers, a pregnancy is a gold mine for a retailer, because that's when your elasticity in terms of what you spend and how much you spend just goes through the roof. And I know from experience, I had two children, when you have a baby on the way, then money is not an issue, right? So they need to know, because this is the main source of revenue for many of their retailers, and Walmart too. And they spend a lot of money getting that type of information, which is how they, in this case, they direct their customers to the products which are profitable for them, right? So that's very well known. It's been around. In the case that we're talking about here, notice that in this case, the supermarket is using the information about the customer to draw very different types of conclusions. The conclusion is, will they pay back the $300 loan? And today, these are things which are very well understood by banks. They know from metadata like that how to determine the likelihood that you will pay back a loan. So these are things that we will see. I suspect I will be teaching the course on data science and machine learning. I suspect that it'll be me, and then we'll talk about that from the technical point of view. But today I'm focusing on the business. And this is the new thing that's coming. By data, we mentioned this morning that data was numbers, then text. Now it's sensor-driven data, what's called LMMs, large multimodal models. Okay, but metadata is a very important data, which is the relationship between the data that already exists in your system. If you lied about your profession, very likely the supermarket knows. If you are a high-income earner, they probably know without you telling them, just because of what you buy, right? If you lie about where you live, they will know, and that lowers your score. If you told the truth, they know, and that increases your score. And the bank has access to that to develop a new business, which is the credit business. Now, this is creating very interesting connections between different companies. Of course, big corporations, they like to be everywhere. Walmart, they're here and they're there. The smaller corporations, they focus on the data or they focus on the retailing, and then they do deals with others to create new businesses based on the information that exists. And this is where a lot of the new information is, in the relationships between data. This is what's called metadata. It's not just the data itself, it's the relationship between this and something else. All right, so excuse me. All right, so these are the issues that that we have to deal with when we deal with data. I'm not going to be dealing with these issues in this course. I suspect we're not going to be dealing with these issues in this program. I'll just mention them to you. Okay, so you can imagine how the database looks like. Is your name, your address, your profession, and then what you have done. One of my former students, he worked at Instagram as a data scientist for a while. And so the data that Instagram, for example, collects, or Facebook, or you can imagine when you go, but they also, the scrolling speed that's recorded, this piece of data. When you stop, when you continue, how long you stay on a particular post, this is all recorded, and it's all part of the database. I'm told that AliExpress, one of them, Alibaba. I'm told one of those. Sorry?
Alibaba owns the AliExpress.
Sorry?
Alibaba owns.
I know, but it's the app, right? So Alibaba is typically the not the retailer, is the wholesaler, and AliExpress is the retailer. Okay, but the thing is that AliExpress is what we use outside of China. In China, they don't use AliExpress; they use Taobao, which is and it's fantastic. It's fantastic, but you need to know Chinese to use it. I was told that one of them, they use the camera. You give permission to the camera, and then the camera will actually look at your eyes, and they know what you're looking at. They will be able to guess what section of the screen you're actually looking at, and how you move your eyes. And so this is all data that's being collected, and this data which is being monetized to enhance their product. We're going to see a little bit about that, okay? But in this particular case, focusing on this example, there's some very interesting considerations about the data, because let me ask you, this is a rhetorical question, you don't have to answer. These are the things that I don't know, and I don't know if they will tell me if I ask, but who owns the data? Well, clearly the supermarket owns the data, but do they send it to the bank? Or does the bank have to query the database, get an answer, but don't see the data? Is something which is, I don't know. It changes the algorithm. Sometimes these algorithms have to be done in the dark, meaning you have to query the database, but you don't see the data, because the supermarket does not want the bank to know the name of this customer. But then the bank is going to say, well, if I don't know the name of the customer, how can I decide? So no, you have to decide with looking at the name. Can I see where they live? So no, you cannot see where they live either. Then how can I decide? Well, query something different. Ask me if, for example, I believe where they live, and I give you yes or no. You understand what I'm saying? Sometimes this data protection, not laws, but business practices, which companies sometimes, it's their data, they don't want to share with anybody, right? So that's an issue. I will mention later something else, which is there's an algorithm that exists that now you can share data with someone in an encrypted way. So I can give you the data, but you will not understand what the name is. You will not understand what the address is. You will not understand the annual income if I know what it is. But if I give it to you encrypted, how can you make decisions if you don't understand what it is? The thing is, now there's a way to encrypt data where if you have a certain function, a certain mathematical expression, which results, for example, in bigger than or smaller than, I can encrypt the data so you can do the same mathematical expression without knowing what the data is on the encrypted one, and the answer is the correct one. For example, this is, we're not talking about this. I just want you to know. Let's say that I encrypt the salary of my customers, and I give you the encrypted version. And well, there's no way for you to know what that number is. But if you tell me what the algorithm is, for example, this bigger than 50,000, then I can encrypt it so that if you want to know if it's bigger than 50,000, my encrypted data will satisfy that property. If you want to know whether, and you can make this in very complicated mathematical, of course it's very easy to encrypt, maintaining that very simple relationship. But if you want to make this much more complicated, for example, this is very important for health companies. You know, I want to know if you have a high blood pressure and this, and you've had a heart attack, and if you tell me what your decision variable is, I can encrypt the data so you will never know what the data is, but the answer to your algorithm is the same. This is called homomorphic encryption, and we know that it's possible, right? So a lot of these things have been created around this concept of working with data in a way that I can share without disclosing what the data is, right? Because sometimes I'm working with someone else's data. And the example of the supermarket and the bank is very clear. The supermarket will not want the bank to know who the clients are. Yet, they still want the business from the supermarket, from the bank, because the supermarket will make money off the credit given to the customers. I think you understand what I'm talking about, right? So this gives rise to many, many issues. One of them is, for example, I say here, subject to manipulation. How do you know that, how does the bank know that employees from the supermarket could decide to create false records so that they can screw the bank? They can ask for loans they will never pay back based on false identities, for example. So the bank has to take care of that. How do they know that this data is not going to be, if they send the data to Canada, from Chile to Canada, how do they know it's not going to be intercepted? Because this data is very valuable. All of these issues are issues which are important today. Okay? And they have to be dealt with in this issue. So you can imagine that. Now there's one topic here that I don't believe is covered in FIM. And that's cybersecurity. Am I right? Cybersecurity is not.
I don't think so.
No, but it's very important. So at least let me spend one slide on it with you, which is, there are two things. Cybersecurity has many different aspects, but there's two that matter to me today for you to know. One is protection, and the other is compliance. Protection is, how do you protect your systems? And there's a lot of people working on that, and passwords and security and two-step authentication and all of that, and secure service. But the other one, which is very important, is compliance. What happens if there is a breach? You have to follow process. And there are new jobs being created in companies where there are people who are hired whose job is just to ensure that all the doors are closed, all the windows are closed, that the proper measures are being taken. People change their passwords, or passwords are well chosen, and this and that. This is a whole new area where people of your skill sets are actually being employed, and they're changing very rapidly, very rapidly. Okay, and another aspect of data is what I call the data virtuous cycle, which is, if you happen to have good data, the good data allows you to create better analytics, which then turn into better products, which then turn into, using artificial intelligence, which turn into more users that increase data. And this creates a fantastic barrier to entry of companies that once they get into this data spiral, it's very hard to compete with them. We talked about ChatGPT this morning. ChatGPT has no particular advantage, except they were the first LLM that people signed up for, and because of that, they're going to be doing this better than anybody. So their advantage is that they were there first. So they were able to create these better analytics and better products because they have access to data that no one else had before. So although their business model is just as good as anybody else's, the fact that they have this data virtual cycle at work earlier gives them an advantage. You know that there's another LLM called DeepSeek. Are you aware of DeepSeek? You know DeepSeek? Yes? Okay. So DeepSeek came much, much later. But DeepSeek has a tremendous advantage. You know what it is? I think every school in China uses DeepSeek now. And schools in the United States are against the use of ChatGPT. So who's going to benefit long-term from their user-generated analytics? I think it's DeepSeek. They have 1 billion people giving them data constantly, whereas ChatGPT is very slow. They were first, but they are very slow at growing. And in fact, a lot of the resistance from this first world of using LLMs is putting ChatGPT at a disadvantage. So ChatGPT's biggest drag for their business model is that their consumers, their customers, are the ones who don't really like to use the LLMs. Whereas in China, people love LLMs. And children are encouraged to use LLMs from an early age. And that trains the systems very, very well. You understand what I'm saying? So now let me go back to a country like Georgia. How is the use of LLMs in Georgia?
And it was not encouraged even in our university.
It's not encouraged here?
They disallow it, I think.
Okay, so
And they encourage it.
okay, so let me tell you, for my course, as much as you want. LLMs, as much as you want. I already told you in this first assignment that I want you to do. First part is all LLMs. They should do that. The second, you have to do with the assistance of LLM, but I want you to tell me what you think. So you have, I don't care. I'm not suggesting this for the sake of training the LLMs. I couldn't care less. They are fantastic tools, and you should use them. They simplify work, and they actually are great tools for discovery and learning new things, right? So, but that, going back to the way these business analytics work, this is the reason why ChatGPT, although they were first, they may lose market share because their customers make this virtual cycle very, very slow, very, very slow. Okay.
But in terms of the users, I think ChatGPT has still the most users than.
I don't know that. I don't know that. I do know that in China, every school is using DeepSeek. So my guess would be that today, DeepSeek may have more users than ChatGPT.
But like, is
Undisclosed,
the
but
right demographic for the LM training?
sorry?
Is the school a right demographic for LM training? Is
I don't know.
that valuable from a kid who's asking about? Like,
Oh, no. Oh, sorry, I'm not saying that only the schools use DeepSeek. No, the government of China is proposing to use DeepSeek everywhere. In particular, the schools are using that. But I think every government agency is using that too. And many old companies are using that too. I don't know. But anyway, I'm just giving you a framework to understand these things. I don't care about the conclusions. Maybe DeepSeek will disappear tomorrow. I don't care. That's not what I'm talking about. What I'm talking about, this gives you a framework to understand how these advantages which are created by data could benefit you in the short, medium, and long term. This is what data does for you these days. Okay? All right. So the conclusion I have from here, and then we'll take a break and then we do more, is I can never stress this enough. It pays to be smart. Okay? You always have to be smart. Knowing a lot is good too, don't get me wrong, but you have to be smart. And I cannot tell you how to be smart. You just have to always be there, always be smart. And I want to de-emphasize the importance of an algorithm. To have an algorithm is never enough. Today is never enough. You need to have good data to go with the algorithm, or you're at a disadvantage. Mathematical structures save time. Without a mathematical structure, Google would not work. The problem is untractable, it's just too big. Mathematics makes it manageable. Okay? And that's why we need to know math. Because math gives you leverage, gives you speed, it gives you ease of solving problems. Okay? But it's not the only thing that matters. And this one is a bit controversial. I'm not going to push it too much, but for me, I think time is more important than money.
For us, maybe.
Interesting you say that. What do you mean?
For a young person, I think it's more important to dedicate time to learning more and not thinking of like earning money,
Well,
for example.
for sure, you have more time than I do. You're going to live longer, and you're not as busy as I am. So certainly this works in your favor. So just be aware of that. Okay, so we're going to take a break now, 10 minutes. When we come back, I will see how all of this affects financial markets. I'll go to finance now, and I want to talk about the music of financial markets, one of my favorite topics. Okay. So I want to now, so I talked about Google, I talked about Scotiabank, and now I want to go back to something slightly more academic, which is to understand how data works in when we are doing finance. In a certain sense, it's the same thing we have seen. We're going to be like Google, we're going to be like Scotiabank, we're going to see how data can help us understand what's happening in the markets. And I want to start with the question. So you have invested in stocks,
Yeah.
right? And you're the only one. The rest of you, no. But imagine you have. You haven't. I don't know if you can imagine or not. But here's a question I have. Say you are a stock investor, and I want to ask you a question. Imagine that you're a stock investor, and I tell you that the stock index went up today. Are you happy? Is that good for you? You invested in stocks. Are you invested in stocks now?
Yeah.
Okay, so if you're invested in stocks, I assume you're going long only, you're not short, right? So if you're investing in stocks and say it was a great day in the market, the stock index went up by 10%, you happy?
Depends on the index. What index are we talking about?
Depends on the index. Depends on the index, exactly. So in which stocks, I mean, give me an idea of the jurisdiction. American stocks, okay, so I told you the American index went up. The S&P 500 went up by 10% today. You happy?
I'm happy, yes.
You're happy, yes. Okay, so the question is why?
Because I'm exposed to markets. Also, my portfolio's correlation to market is very high.
Exactly. The portfolio of your investment to the stock market is very high, but you've never calculated that correlation.
I did.
Oh, you did? Okay, well, you are ahead of the curve. But okay, so even if you have not calculated the correlation, there are still reasons for you to be happy, because this is a fact, and that's what I'm going to be mentioning now. It doesn't matter what you invested in. It doesn't matter what you invested in. Most portfolios that you invest in will have high correlation with the market, whether you want it or not. In fact, it's very, very difficult to find portfolios which will not have very high correlation to the market. It's very hard to have an investment in stocks, long. It's very hard to have investments in stocks that will perform differently from the index. It's a fact. But I want to get into that fact. I want to say why. Why is that? Do you all understand what I'm talking about? Okay. I'll give you another, so let's say that you, actually maybe this is related to what we discussed yesterday in our snow fund example. You are in Kutaisi, you have to go outside, and they tell you it's raining in New York. So you bring an umbrella. But I tell you it's raining in Tbilisi. Should you bring an umbrella? Perhaps, right? It's more likely that the weather in Tbilisi is more relevant for you than the weather in New York. So what I'm talking about now is these types of situations, which is we want to understand what are market factors, which is what things will make a difference to you, and focus on investments. What factors that I can easily identify will make a difference on your investments. Okay. And I start with the simplest and my favorite, which is the fixed income markets, interest rates, bonds, loans, things like that. And this is an exercise that I asked my students to do when I teach quantitative finance. I'm not teaching quantitative finance now, so this is not an exercise you're going to do. That's why I lecture about it. If this was the other course that I did, I would ask you to do it. But maybe some other professor will tell you to do this, although I don't think so. This is not an exercise that many people do. Many people ask students to do, but I always do. It's so important that I have to tell you, because you're not doing it. So imagine that you have these yield curves. I don't know if you know what a yield curve is. I will explain to you what a yield curve is very soon. But do you know what a yield curve is? You know what a yield curve? Do you know what a yield curve? You know what a yield curve? So this is basically the interest rates that are charged at different points in time. The interest rate for the 1 year loan or bond is different from the interest rate from a 5 year. Okay? Typically, the longer you go, the higher the rate is, typically. We'll talk about this. This is not something that you have to be. Just bear with me. So imagine I give you 3 curves, which are like that. The red curve is today, the green curve is tomorrow, and the blue curve is the day after. Can you see the colors from there? You can see the colors, right? Yeah, it's very bright, but you can still see, right? What do we see that? What do we see there? So we see interest rates are growing. We also see that they're growing faster on the short part of the curve than on the long part of the curve, right? You see that? Okay. Imagine instead of 3 days, I give you 2 years worth of data. So there's 400 curves there. Of course, you cannot see them. You need a computer to analyze this. That's why I like to use this visual approach with only 3. How would you know what's happening? How can you tell? Back to the example, I asked you about the stock market and the stock index. And you understood the question and you gave me an answer. If you had now a bond portfolio and I tell you this is what the market is doing, how do you know how to react to that?
I would calculate the average.
Sorry?
I would calculate the average.
You will talk?
I would calculate the average.
The average of what?
Of the curves.
No. Okay. So thank you for the answer. Thank you for the answer, but that's the wrong answer. And that's what I want to tell you. Okay? So this is how data science enters financial markets. It's in a slightly different way from what you said. Okay? So to analyze that, it turns out that we have the ability to do a decomposition of these moves, not by the average, but by something different, which is, first I'm going to tell you what it is, and then I'll tell you why it's like that. So what it is different. The motion in the fixed income markets is a little bit different from the stocks. It's not the average that matters. What matters is this. the movements are a superposition of three main factors and then others. The first factor is what's called the parallel shift. The parallel shift. That will be the average of the changes of the difference. Okay, so if you look at the difference between the red curve and the green curve, the difference, you take the average of that difference. Maybe that's what you meant. Doesn't matter. What you look is at the average of that difference. You see that the difference between the red and the green curve is high at the beginning and is low at the end, right? So you look at the average of that. And the same thing would happen to the difference between the green curve and the blue curve. You look at the difference and you average that. And then you average the whole thing. That is the most important factor. And if you are a bond investor, you will look at that number. Okay? Now, that's going to be the main factor that affects you. But the second factor that affects you is something that I can also calculate, which is the following. I'm explaining this in a visual way, but then I'll give you the mathematical formulation, which is much easier to understand. But first I want to do what's called the heuristics, or the intuitive approach to this. So the intuitive approach to this is, the second factor that matters is what's called the tilt. And you can see here how the yield curves are tilting. I don't know how to calculate it yet, and in fact, maybe I don't care, but you can see that the tilt, whatever the tilt is getting, when you go from red to green, we agree that red was today, green was yesterday, and blue was the day before. So when you go from red to green, you can see that the curves are moving that way. Okay? And from green to blue is the same thing. So the 2 days that I have changed here, it moves in exactly the same direction, like that. So if the direction is like that, and I will tell you what like that means mathematically in a minute, we know that the second factor is positive on the 1 day change and positive on the second day change. The third one, this is getting silly, I know, but I'll give you the mathematical description later. Just hold on with me a little longer, okay? And the third one is something which is called the convexity, which is the curves we can barely see, but maybe they do this other motion here. It's known that this motion matters. It's very important. Every bond investor knows that beyond this and beyond this, this matters. It's called the convexity, or something called the butterfly spread, because it's like a butterfly. Okay? We cannot see it. At this point, I can define it for you mathematically, and I will. But I just want you to have the intuition that first is the parallel shift, then is the tilting, and then is the butterfly. And these things affect financial landscapes very importantly. As you know, this is how monetary supply is managed. When central banks want people, corporations to have money, they try to bring rates down, right? That increases money supply. For example, if you are on the brink of a recession, to prevent a recession, central banks like to bring rates down. That prevents recessions. I don't know, do you follow the American news? Okay, so have you seen how Donald Trump has been fighting with Jerry Powell to get the Fed to lower rates for a long time? That's what he wants. He didn't say, I want the 1 year rate to go down, or the 2 year rate to go down, or the 3. Doesn't matter, because we know that the factor that matters the most is rates from a parallel shift perspective. Just lower them all. Because once you lower one, they all tend to lower. Okay? You understand? Okay. This is intuition. I want you to have the intuition before I tell you the math. The second is the curve steepening. When the curve steepens, is typically when you get into a growth part of the economy. And when you get into a recession, typically the yield curve flattens or even becomes inverted. So the second factor measures something very important, which is whether I'm going into a recession or not. You can read off economic information from the second one. What about the third? Complicated. We're going to leave it there. You get the sense, right? Okay, now, all of this is very nice, and maybe I can lecture on economics with this, but I've been just hand-waving my way through this. That's not the way we do data science, not in this course. So I need to turn this into things that you can measure, algorithms. You can put it into a computer, get answers. The answers you will understand, and you can act upon them. Just like Google did what they did, just like Scotiabank developed that, we're about to develop our own way of understanding markets. All right? And I'm starting with the fixed income market because it's very easy to understand. I'm going to go to stocks next, but I want to start with fixed income. So this is the intuition. Let me turn the intuition into math now. To turn the intuition into math, this is what I'm going to do. My source of data is going to be the yield rates. I don't care that you know exactly what they are. I will tell you what they are. Maybe on Sunday, I don't know when. I will tell you what they are, but for sure this week. I mean, for sure before I go. This is something that I want to be with you when I explain it. This is not something I want to do on Zoom. So the yield rates are things which are measured as follows. Every day you have rates, but every day you have the 1-year rate, the 2-year rate, you have the whole curve. So in the case of rates, every day you observe a curve. In the case of stocks, every day you observe a number. In the case of rates, every day you observe a curve. And the curve moves from one day to the next. So just like stocks are tracked with graphs, which are points over time, the fixed income markets are graphed with surfaces, which are curves over time. You know that? Okay, fine. So this is going to be my input data. Every day I have rates for certain periods of time, 1 year, 2 year, 3 year. Okay, so they're moving vectors. What I'm going to do is every day I'm going to look at the change, the percentage change between today and yesterday. That's what I have there, the percentage change. Every rate will have a percentage change. Note there that I have two time variables. Lowercase t, that's the time today. And uppercase t is the rate that I observe, 1 year, 2 year. Two time variables, important not to confuse. Lowercase t is the today, tomorrow, day after, or today, yesterday, the day before. That's lowercase t. Uppercase t is 1 year rate, 2 year rate, 10 year rate. Each of those rates changes from day to day. The percentage change is what I track. So this is something I can calculate. The formula is written there. I track this on my database in my computer. You picture that, yes? Okay. By the way, the assignment I ask my students to do every year when I teach finance is they need to track this curve for 2 weeks, every day. Put it on a database and do all of this analysis themselves. I'm just telling you what they do, because this is not that course. Now, once you do that, you have here a number of variables that change every day. Now, these are going to be random variables. This is the first time I introduce some context of probability, but you know that. Random variables because each of them moves every day. So these variables give me a variance-covariance matrix. I have here a random vector. I have observations daily of this random vector. So the vector will give me variance and covariances. And I assume you know what they are. I'm not terribly concerned because we will see them probably tomorrow. I will give you the definition of these things, but I suspect you already know what they are. Yes? Okay, so these rates Think of the red, green, blue curves. From there, I can get a time series like this. I had 4 rates in those curves, so there are 4-dimensional vectors moving, and I have 2 of them. That means for each of those 4 rates, I have 2 days observed here. 4 rates, 2 days. To do statistics with 2 observations is not very big, but I can still do it. So the resulting matrix for the colored example I gave you will be a 4 by 4 matrix, where the covariance and variance are calculated with a statistical sample of 2 days. We had 3 curves, but because we look at differences, I only have 2 differences. Okay? So I use the 2 differences to calculate the variance covariance matrix of 4 curves. So when I look at the variance covariance matrix, the length of my time series does not appear. What appears is how many rates, the number of variables I'm looking at, and it's 4. 4 by 4. Okay? So from that variance covariance matrix, this is what I'm going to do now. I'm going to look at the eigenvalues and eigenvectors. Here they are again, but now you've already seen them. I don't have to explain eigenvalues and eigenvectors again. You saw the video earlier, right? The values are positive. So I can think of which one is the highest. And typically, in this context, lambda 1, the first value, is considered to be the highest. They are ordered so that lambda 1 is the largest, lambda 2 is the second largest, lambda 3 is the third largest, and so on and so forth. Okay? That lambdas give me the size, and V are the actual vectors. V1, V2, V3. So to my students, when they take my course, I ask them to calculate V1, V2, and V3. And I tell them what V1, V2, and V3 will be. And I'm going to tell you what they are, because they're always the same. When you do this analysis, the V's always end up being the same. Let me tell you, this is very important. They're always the same. So, I'm going to look at the fixed income market in Thailand. They are the same. I'm going to look at the fixed income market in Japan. They are the same. The US. If you have a fixed income market in Georgia, I don't know how many bonds you have in Georgia, they will be the same. They're always the same. Because this is an economic invariant. I said this morning that every time you have an invariant, something interesting is happening. And if, not mathematically, in anything. When I move something around, something is left invariant. That's the eigenvalue. And something interesting happens. It's called the axis. That's how you build cars. They have an axis, and the wheels move around what doesn't change. Right? So every time you see something, an invariant is an important thing. The law of conservation of energy. Have you heard that in physics? Yes, you do. When I drop a ball, the kinetic energy plus the potential energy is constant. That's a very important law. With that law, we can send something to the moon because it tells us a fundamental principle of physics. Once energy is conserved, then I can start to calculate the equations of motion. Right? That's another example of something that doesn't change, an invariant that tells us information. Most chemistry is also conservation laws. Conservation of mass, conservation of whatever. Airplanes fly because air does not like to be compressed. Boats sail because water is even more incompressible than air. right? So every time you have something that doesn't like to change, something interesting happens, always. And an eigenvalue is just a reflection of that. It's just the mathematical way to calculate what doesn't change. And the popularity of websites is another example of that. So back to fixed income, I'm just trying to get you to understand the universality of this. We're surrounded by eigenvalues and eigenvectors. We're surrounded by things that don't change. We're surrounded by invariants, and invariants matter. Because if I can understand fixed income markets in Thailand, in the United States, and in China in the same way, that makes me very powerful. Because I see something that no one else can see. And that's what eigenvalues will do for us. So let me tell you what they are. The first eigenvalue, V1, is the eigenvalue which is 1, 1, 1, 1, 1, 1, 1. What does that mean? If you knew a lot of mathematics, you will immediately know what that means. But now you have the intuition, so maybe that's good enough. If I tell you the first eigenvalue is 1, 1, 1, 1, 1, what does that mean? That means that the most important movement in a fixed income market is the parallel shifts. 1, 1, 1, 1, 1. They all move the same. That's why Trump wants Jerry Powell to lower rates. He didn't say lower the first-year rate or the 5-year rate. He just wants rates lower because they all move together. And that's reflected on the fact that V1 is 1, 1, 1, 1, 1. Not exactly 1, but you know what I mean. 0.9, 0.8, 1.1, right? Now, what's V2? You can probably guess what V2 is, given what I told you earlier. Is the tilting. So what vector represents tilting? What vector represents tilting?
0.7, for example.
It's a vector. And it's a vector of, say, 4. 1 year, 2 year, 3 year, 4 year, 4. So 1, 1, minus 1, minus 1, how's that? That represents tilting, right? Or you can say, okay, 2, 1, minus 1, minus 2. That represents tilting, right? So V2 will be like that, tilting. V3 is the butterfly spread. And these are things that, as you can see, you can calculate. I just told you. I didn't ask you to collect the data. I didn't ask you to calculate the returns. I didn't ask you to calculate the matrix and then get me the eigenvalues and eigenvectors. I asked my students to do that, but I didn't ask you to do that. But I'm telling you the result of that. Because markets are always like that. Fixed income markets are always like that. Okay? All right. Now, let me move to stocks now. Let me move to stocks. When I move to stocks, I don't have rates, I just have numbers. Rates are a curve every day, a different curve every day. Stocks is a different number every day. Let's do the same. I only have one number, but I have many stocks. If I look at all the stocks moving at the same time, I can calculate the returns of each stock, like before, and I can calculate the correlations between stocks. And therefore, I can have a variance-covariance matrix of stock movements. You understand what I'm saying? All of this will be defined tomorrow or the day after. I'm not waiting for the definition. I prefer you to get the idea first, the definition later. So I can have the variance-covariance matrix of stocks. You told me that you calculated the correlations of your stock portfolio with the market. Well done. Maybe you also did the variance-covariance matrix of your stocks.
No, I haven't.
No, it's okay. You could have, it doesn't matter. If you did the variance-covariance matrix of your stocks, let me make an assumption. Let's say that you invested in 10 stocks. I chose 10 because I have 10 here. Okay, I want to claim these are your stocks. I don't know. But if you invest in 10 stocks, you're going to have a variance-covariance matrix which is 10 by 10. Yes? Great. Now, don't look at the variance-covariance matrix as it is, because the variance-covariance matrix does not carry, has a lot of information, but it's hidden. If you look at it, you can stare at the variance-covariance matrix for a day and you will see nothing. But if you write your variance-covariance matrix using eigenvalues and eigenvectors, you see everything. They are very telling. And that's what I have here. I have the variance covariance matrix written as eigenvalues and eigenvectors. Let me show you. Maybe I should stand up, I don't know. I'll stand up. I'll show you. There is over 100 numbers here. I don't claim you understand anything, but by the time I'm finished, you will understand everything. You will see the meaning of every one of these 100 numbers. This is linear algebra that I'm doing. It's the same linear algebra that you learned back then, but I'm applying that to stocks. Okay? All right, so here we go. I have taken all your 10 stocks, and I have done the variance covariance matrix, which I don't show you, and then I have done the eigenvalues and eigenvectors. And this is what I came up with. My first eigenvector is 2.027. My first eigenvalue, sorry, sometimes I mixed it. The first eigenvalue is 2.207 times 10 to the minus 3, that's not important. And the vector, the eigenvector is minus 3.2, minus 3.5, minus 2.4, minus 3.16, and so on and so forth. Let me stop right here. What strikes you as important when you look at this first vector?
All are negative.
Actually, that's not important, because you should remember that when you calculate an eigenvector, the eigenvector can be multiplied by any number, and it still is an eigenvector. So 1 is an eigenvector, 2 is the same eigenvector, 3 is the same eigenvector, because eigenvectors represent directions. If I have a negative number there, it's because the computer follows an algorithm to get me this. And the algorithm does not control if I get minus, plus. I could get this number multiplied by 1,000. I could get the number 32 million and 35.9 and 24.3, and it's exactly the same eigenvector, because eigenvectors represent directions. You remember that? Yes? Eigenvalues represent direction. You can multiply an eigenvector by any number, and they don't change. Eigenvalues, no. Those are absolute numbers. But the vectors you can multiply by. So the fact that it's negative doesn't matter. It could be positive, or you can multiply by a million. It doesn't matter. What's important is that they're more or less all of them the same size.
Yeah.
You can say, well, that's the lowest one. 14 is the smallest, and the highest is maybe 3.8. But they still are very comparable. I consider them to be the same. So let me stay right there, because that tells me that this first eigenvector gives almost equal weights to all the stocks. So it's almost like a parallel shift. All the stocks move up and down by the same number. Which, by the way, is the reason that you said that your stocks are correlated to the index. There's another property that's a bit more sophisticated. Maybe you didn't see that, but the first eigenvalue of a variance covariance matrix is very highly correlated to the random variables that give rise to it. We'll see that. So that's the reason. And it's called the significance. The percentage of the movement that the first eigenvalue gives is the ratio between that value and the sum of all the values that I have here. These are all the other eigenvalues. This number is 55% of the sum. So a single number explains 55.7% of the movement in my stock market. That's what that 55.7 means. Okay? So that number 2 is not important. What's important is the division between 2 and the sum of all of them. The sum of all of them is about 4. So this is about half. That's a lot. Of 10, that one of them is 50% of the other 10, of the other 9, is a lot. And of course, this explains a lot of the movement of the stock market. When you do the parallel shift in the fixed income market, the first factor also explains about 50%. It's about the same. So there's a lot of weight, a lot of significance given to that first value. Okay? Okay, let's go to the next one. The next one, you can see now explains a lot less. If it was 50%, this is 10%. It only explains 10% of the resulting move. So it's not very important. But let's see what it is. When you look at it, what do you see? What you see is that it's essentially one number, one stock. This one. This one is much bigger than the rest. So the second factor is that stock. Now I don't know what that stock is, but likely this is a stock that has done something very strange. If this was data over the last 2 years, that would probably be a stock that has done something very strange over the last 2 years. So let me tell you what this data really was. This data was not your stocks. This data was 10 German stocks. And very likely, this one stock here is a stock called Wirecard. Have you heard of that? Yeah. Wirecard? Do you know about Wirecard?
Yeah, they know.
Do you know about Wirecard? You all know about Wirecard? No. Tell him Wirecard.
Wirecard was a fraudulent not a financial services company in Germany that was growing in very high digits, double digits, and then was lying about its subsidiaries in Asia, and they stole a lot of investors' money, and they were accused of fraud for many years by Wall Street Journal or Financial Times, and they finally couldn't prove where 2 billion left, and they crashed, they failed. Everybody was arrested, and one guy fled to Russia and now works for Russian KGB.
Okay, well, that's a good story. If I tell you the mathematical story, I will tell you Wirecard is the second eigenvector of the variance covariance matrix. In fact, if that story had been an even bigger story, maybe it would actually have been the first eigenvector. Do we get a sense now what eigenvectors mean? They give us meaning. Eigenvectors give us meaning. They help us take a lot of data and understanding what's really important. And the rest is not important. Once I go to this one, that explains 7% of the movement. And if I go to the last one explains less than 7 per thousand of the movement. This is nothing. This is just garbage. It's noise. There's nothing interesting happening here. In fact, I suspect everything from here down is just noise. We don't really know. I would not even trust these numbers. They will change from day to day, but this number is not changing. And the Wirecard story is not changing either. Understand? Okay, let's reflect on this. Let's reflect on this. What do we learn from this? What do we learn from this?
That eigenvectors and eigenvalues are very important.
One of the important things in life, and one of the reasons that data science exists, is we want to understand why things happen. And we want to understand what helps us understand why things happen. In a few months, I will give you a course on data science and machine learning. And one of the things that we want to do is we want to understand what makes something detectable. When I do face recognition, do you know how face recognition works? Face recognition looks at your face and knows what features in your face will distinguish you from her and from him. But it's the same thing. This is just a simplified version of that. There's a term for that in machine learning. It's called feature engineering. That's the modern version. Back when the world was linear, because this is a linear world, feature engineering is done with eigenvalues and eigenvectors. Okay? So this is the way we have to understand how to simplify the world. Simplifying the world is very important. And that's what data science is used for. You have a huge customer database, but something there tells you that he is telling the truth and he is committing fraud. Same thing. Or if you want to know, is she pregnant? Well, some indicator will tell me if she's pregnant. It's the same thing, you see? It's the same thing. We're applying that to the financial markets. And we saw two examples of doing that with the bond market and with the stock market, things that we understand very well. Now we can take these two areas that we don't understand very well. This is very simple, and I can do this with traditional mathematics, eigenvalues and eigenvectors. If I wanted to do something different, for example, imagine I want to know if people like Facebook. In fact, I did that. I have a paper on that. Do people like Facebook?
How do we measure it? How do we measure it?
How do we measure it? So this is a very important problem for which we use data science for. And we want to understand features. And with the feature comes the significance, and then comes with the feature itself. So in this case, the feature is the principal component. This is the traditional name today. We call them a feature, the main feature. And this is something that we can take to other circumstances. We can take this to understand market factors that will help us understand how securities move. So this, I think I told you that. So I'm just telling you the things that I already said. I want to move on. And this is the comparison of two markets. I'm comparing here the stock market with the hedge fund sector. The hedge fund sector, do you know what a hedge fund is? I'll tell you what a hedge fund is in very simple terms. When you invest in stocks, you went long. You invested in stocks only going long. Imagine that you go to stocks long and short. You buy some stocks, you short some other stocks. Then that's what hedge funds do. Now, the fact that the significance here for stocks is much higher and then drops is because stocks are all the same or very similar. They have similar characteristics. But hedge funds, because they buy and sell, they go long and short, they remove a lot of that dependency. And now, so they have less significance, okay? But that's less important. Let me go to this. Because this thing that we are mentioning here is a very good example of data compression. And data compression is a very important topic today. I want to explain to you now how music or sound is compressed, to find yet another analogy. As you can see, there's a theme today. We started with some reflections about new businesses and value creation, then Google, then the bank, then fixed income markets, then stock markets, and now I'm going to end up with music, really sound compression. Okay? So, and it will be exactly the same. It will be exactly the same. So first I need to tell you do you know what sound is? Sound is a wave. Okay, sound is a wave. Light is a wave. And waves move according to a certain very well-known equation. This is the, well, okay, this is there, the equation is the wave operator. The wave operator is essentially the second derivative. Okay, the second derivative tells me the speed at which, it actually not the speed, it tells me the acceleration at which the wave moves. It's very well understood. But for us, what's important is that this operator tells me the acceleration of my waves. It's called the wave operator. Now, the wave operator for sound has eigenvalues and eigenvectors. Let me first calculate the eigenvalues and eigenvectors, which are very easy, and then we will interpret the eigenvalues and eigenvectors. So this is an eigenvector, and that's the eigenvalue. Why? Because the wave operator acting on that eigenvector, you know the second derivative. What is it? Right? So it's n squared times the same function, sine nx. Right? So this gives me, acting on that gives me that. Now, some considerations here. We have seen eigenvalues and eigenvectors on matrices. Some of you may be asking me, where's the matrix? Do you see a matrix here? I will argue with you that that's my matrix. The second derivative is my matrix. It's an infinite dimensional matrix. I don't want to lose you now. I don't want to lose you now. I need you to understand this. A derivative is an infinite dimensional matrix. Let me see. What is a matrix? It's a transformation. Don't think of a matrix as a bunch of numbers. Think of a matrix as a transformation. You give it a vector, give you another vector. Right? So if you allow me to say that a function is a vector but of infinite dimensions, if I give a function to an operator, to a derivative, and it gives me a new one, then that's exactly like a matrix. And in fact, what I'm telling you is actually true. Infinite dimensional matrices are operators like that. So let me carry that analogy further. If the second derivative is a matrix, the sine function is the eigenvector. And the eigenvalue is the number n squared. Okay? Now, is that n squared? We always talk about the largest eigenvector. The largest eigenvector is not going to be infinity, because they get bigger and bigger and bigger. So let's not worry about the biggest. In fact, let's look at the smallest because of the minus sign there. Okay? So the smallest eigenvalue will be n equals 1. N equals 0 will work, but then the same function is 0. So I don't like to have 0 eigenvectors. I prefer to have non-zero eigenvectors. So the first one is 1. Right? And now I'm going to make a picture. I have a picture here of all of the eigenvectors. And I have them color-coded for a particular reason. Let me do this. The first one is the black one. You see the black one? That corresponds to n equals 1. Is the sine function. And I'm taking this length to be 2 pi. Yes? That's n equals 1. Then I have n equals 2. Also in black. Okay? And you see it crosses at exactly half the point. Then I have the third one with n equals 3, which corresponds to the first red line that we have there. And it crosses that 2 times. Then I have n equals 4, which also is in black, and it crosses that 3 times. Then I have n equals 5, and that's in blue. And then I have n equals 6, which is in red again. and then I have n equals 7, which is in green, and then I stop. But here what you have is the superposition of all of these eigenvectors. Yes? Okay, why am I telling you this? I'm telling you this. This is how music is compressed. Do you know the MP3 technology? You'll have an MP3 player in your pocket. This is an MP3 player. How is music digitized? Do you know? You record the sound, and then the sound is turned into zeros and ones and put inside your phone. What's the process of taking a sound and bringing that into zeros and ones to put into your phone? Do you know?
I think so.
It's exactly this. A sound is taken, a sound has a certain vibration, so a certain function that vibrates, and something called the encoder, sorry. Something called the encoder is an electronic equipment. It gets that sound, which is a vibration. I said, that sound is a little bit of n equals 1, a little bit of n equals 2, a little bit of n equals 3, a little bit of n equals up to 300. And then you keep those numbers. That's encoding. And how many of these numbers you take is what's called the bit rate. Everything beyond that you chop off. We don't care because we cannot hear it. These things are chopped off where the human ear stops listening. You know that the human ear can only listen up to certain frequencies. Dogs are better, they have better frequencies than humans, right? So for example, the typical MP3 encoder takes frequencies up to 300 megahertz, and then it stops. I have the hertz here. The first one, the black, is 65 hertz. So if I want to go to megahertz, I stop when n squared is equal to 1,000,000. That means n is about 1,000. So I record 1,000 of these numbers through my electronic encoder. It's 1,000 numbers. So I put 1,000 numbers into your phone, and they're right here, taking memory in your phone. How do you play it back?
Decoder.
Exactly. Now you use a decoder. And a decoder takes, okay, give me all those 1,000 numbers. I'm going to make the sounds that corresponds to each of these numbers. That's what the decoder does. And I'm going to play it back, one on top of the other, because sound is linear. And then when you play them back on top of each other, they sound exactly as the original. The difference you cannot hear. That's how music is encoded. This is the MP3 technology. It's exactly that. Now, this is the interesting part. This encoding that we have here is adapted to a very particular type of sound. It's the sound that is created by a one-dimensional vibrating string. Give me examples of one-dimensional vibrating strings. A piano is on a one-dimensional vibrating string. Yes? Others?
Violin.
A violin.
Our voice.
Our vocal cords are one-dimensional strings too. So everything which is a one-dimensional string will be encoded very well with this because I'm using the matrix adapted to the one-dimensional vibrating string. That's why when you play music or you sing or you talk, the MP3 technology works very well. Now give me examples of instruments which are not one-dimensional vibrating strings. A drum.
Okay.
A drum is a two-dimensional vibrating string. Does this work for the drum?
Why? Because of the vibration it gives.
See, I'm encoding the vibration. I'm capturing the main elements of that vibrating object, and I'm storing that with a certain bit rate. If I was able to record all bit rates, then it wouldn't matter, because I have a perfect reproduction of that sound, however weird it was. But if you now give me something that vibrates with other functions which are not sine functions, then I'm going to have it's going to be a slower fit, it's going to be a worse fit. It's as if I'm trying to model a stock market with a fixed income market. It's not going to work very well. My noise is going to be very high. My signal to noise ratio is very low. And I don't know if you listen to music, but if you listen to music, you will see that drums are very hard to listen on MP3s. They sound like not good. Trumpets are also not one-dimensional strings. Very hard to compress a trumpet. In fact, people who do professional evaluation of recordings, they like to look at trumpet passages, which those are, you can actually hear the difference. A trumpet is not a one-dimensional string. It's a complicated three-dimensional manifold. Now, my favorite, applause. Have you ever listened to a recording of a live concert?
Yes.
Have you noticed how the music sounds great, but that noise does not match with what you heard when you were there? Have you noticed? It sounds bad. The round of applause sounds like real noise, like unpleasant noise. The reason is what is that? It's very far from a one-dimensional string for which the MP3 was invented. So most of what was thrown away as noise was actually not noise. All the information was there. That's the wrong wave operator to compress a round of applause.
How many dimensions are there?
How many dimensions?
Yes, what's the biggest dimension?
No, actually it's not so much about the dimension, because see, this is a one-dimensional string. In one dimensions, most instruments are the same. For example, a flute is one-dimensional, but it's not a vibrating string. The flute is very interesting because you have air vibrating, but air goes through one of the ends of the flute unobstructed. It's not vibrating. So what happens is that what vibrates in a flute, here you're measuring pressure. Pressure is 0 for a flute here. But pressure is not 0 for the flute over there. So the operator is the same, but the boundary conditions is that it's 0 here, but the derivative is 0 there. Not the value. Pressure is not 0. The derivative of pressure is 0. That gives rise to something else. It's actually it's sine of 2n and cosine of 2n. It's slightly different, but still very similar. So the MP3 technology still compresses flutes and oboes and all that very well, because they're still one-dimensional. It's called the boundary conditions. Those are slightly different, but it still compresses them very well.
Is there a sound that we can't hear? Is there a sound that we can't hear?
A sound that we cannot hear. A high pitch. When you go up, when you go above, I don't know how many, I forgot how many megahertz, the human ear cannot record that. We cannot hear that. For example, I'm told, I don't know if this is true, that if you kill a lobster, which I do sometimes at home, the lobster is screaming when you boil it, for example. If you hit it, it is unpleasant for you. I don't know if this is. I'm talking about killing an animal. Okay, if you kill a lobster, we have a lot of lobsters in Canada. It is something that. So if you boil a lobster, they scream before they die, and dogs can hear it. We cannot hear it, and apparently dogs find it very disturbing. So yes, there's sounds that we cannot hear, dogs can hear. You probably know that there are whistles that people use to scare dogs that humans cannot hear. There's even, I'm told, I haven't seen them, that there's whistles that have the frequency so that young people like you can hear, but older people like me cannot hear. And they use that to discourage parties. I can sleep through them, I cannot hear them, but they really, really bother you. This is all very interesting. But okay, I'm getting off topic now. Back to what I was talking about, which is I want to tell you about. So let me now tell you why I use this color coding, because this is very interesting now. I'm going slightly off topic, but I want you to understand this because this is significant. This affects our ability to do data compression. I talk about transmission, I talk about speed of computations, I even talk about it's called homomorphic data encryption. That was the ability to encrypt data so that we can do calculations. This is different. It's about data labeling. So that first red line that I have there, the n equals 1, corresponds to what's called the fundamental frequency in music. If you take I'm going to play the piano. Okay. If you take a piano and you play, I'm going to play some. So I'm using a decoder now. I'm using a decoder on my iPad, okay? I'm going to play some music here. Okay, so I have a piano here. And I want to play, it is not this one. This one is a 65 hertz. This is the D key in the piano, which is the lowest D, is way out there. Okay, so I'm not going to play that D because it's very, and on the iPad it doesn't sound very good. It doesn't have a very good decoder, but it's that one. Okay, it's that one. That's that sound. Just see. That one. That would be this one. Okay. Then you have the other one, which is n equals 2. N equals 2 is the sound that happens when that string is half the length. The first half plays another sound, and the other half plays exactly the same sound. So if that was that, the next one with n equals 2 is this one. The length of that string is exactly half of the length of the previous string. That's why pianos are shaped like that. Those strings are very long and these are very short. For a violin, they're all the same length, but the tension is different. And that's why with the same length you play a different sound. But in the piano, the strings are slightly different. That's why, I'm talking about a concert piano, right? They're like that, shaped like that. Oops, what happened? Something. The timeouts are wrong in my computer. The Zoom call disconnects and my screen disconnects. I will fix it. I will fix it. Okay. All right. So now, how about this one which is red? That's n equals 3. N equals 3 is the vibration how we would take a string which is a third of the length. And that has a name. You're the only one who plays music here? You too? What do you play?
Piano.
Also piano. Oh, 2 pianists over there. This is fantastic. In my next trip, I bring the violin. We play something together, okay? Is there a piano in the campus?
Well, there is.
There is? Yes, okay. I travel with a roll-up keyboard. I travel with a roll-up keyboard.
Oh, really?
Yes. I didn't bring it here because I had The airline that I fly to, Kutaisi, has a very serious baggage restrictions, and I have already a lot of luggage. So I carry 50 kilos of luggage with me. So the roll-up piano is another 600 grams, which I just leave at home. But I have a roll-up piano. Normally I travel with it, yes. I don't play the piano, but I sometimes it's very therapeutic to play. When I'm in a hotel by myself for many days, it's sometimes nice. I wish I could travel with a violin. I cannot do that. So, but you don't play music, no? Okay, so this one here, the red one, that's the dominant. So that'll be the G. Is that one? That's the red. Okay, and then when you go to this one, 4, well, 4 is a half of a half. So it's back to C. Except now it's 2 octaves higher. So it'll be that one. Okay, so I'm not gonna continue to go higher, higher, higher. I'll just bring them down to where they are. That's the. And how about the blue? The blue is n equals 5. N equals 5 is a new note. It's not one that we have seen before, which is an octave higher. You know what an octave is? That's an octave higher. The same note, 1 octave higher. Okay? So the blue one is new and is E. That's the one that comes up. E. Okay? And then when I go to 6, well, what is 6? 6 is 3 times 2. So 3 was G, the dominant, an octave higher. So it's back to G. That's this one here. And how about n equals 7? That's new. We haven't seen it before. That's a new one. Happens to be, if I remember correctly, a B flat. And like this, see, every time you hit a prime number, where n is a prime number, is a new note. If n is not a prime number, it's a previous note, an octave higher, or the fifth of a fifth, or something. So you can go back to a previous note that you already had. But every time n is a prime number, then you're going to have a new note. And there's something very interesting here, because, by the way, Pythagoras knew this. I think this comes up next. This is, I call it Pythagoras piano. You know how this was discovered? You know Pythagoras? Yeah. The square triangle? Okay. So Pythagoras used to go to work going in front of a forge. A forge is where they make these things. And they were not making one, they were making several. And some days he would see that, he would hear that the sound of the two noises coming from two different rods where they didn't go with each other, and sometimes they went very well with each other. So he got curious, why is that? And then he discovered that if the ratio between the lengths is close to a whole number, it sounds very good. Like this C and that C. If they're playing this, if they're hitting rods which are exactly twice as long from each other, they sound like that, it sounds very well. So that's, but then other days, he got curious, and then he saw that they're playing these distances which are almost the same but slightly different, like this one. Doesn't sound very good. He discovered that by walking through a forge. So from there he came up with his theory of music. Pythagoras has the first theory of music. Perhaps that's the reason why Western music focuses a lot on harmony, not rhythm. You go to Asia or Africa and it's all in the rhythm. There's no harmony. I mean, the harmony is much less important, but maybe Pythagoras, who was part of the Western culture, he's the one who discovered harmony. And he saw that harmony is related to the lengths of these strings. And then he saw the prime numbers, and then he saw all of that. And then he created the first musical theory, which, which in 1850 became physics. And then in 1950 became the MP3 technology that I'm telling you about. It's all based on the discoveries that one-dimensional strings have a wave operator, a matrix, with eigenvalues and eigenvectors that we can identify. And we can build encoders and decoders adapted to that. See that? There's something very interesting. I showed, if this theory was as I told you, there would be, a piano would not exist because you would have infinitely many notes, right? But in the musical scale, and you guys, I don't know if you know, there's exactly 12 notes that repeat themselves. But where's the number 12 coming from? I mean, every time there's a new prime number, and there's infinitely many prime numbers, every time there's a prime number, then we should have a new note. So keyboards should have infinitely many keys. And forget about the whites and the blacks, there will be, who knows, right? The reason is that 3 to the power 12 is very, very close to 2 to the power 19. What does that mean? That means that after you take the same, the fifth, the three is the fifth, right? Is the dominant. That's when you take a string and you cut it into thirds, and into thirds, and into thirds 12 times. What you end up with is as if you cut it into twos. But cutting into twos repeats the sound, is the octave, right? So what that means that after doing that operation of fifths 12 times, you go back to where you were. So then people realize, well, in that case, with 12 keys, I can have all the sounds. And this is how the well-tempered clavier, the work by Bach, was constructed when this was established. And that's why music notation only has 12 notes, because 3 to the power 12 is approximately equal to 2 to the power 19. And that's where there's 12 keys in the piano that repeat. The repetition is in the number 2. By the way, if you know harmony, that's why you have the circle of fifths. You have a circle of fifths that contains 12 of them. That's how physics is related to music theory. And Pythagoras knew that. So this is very nice because you also know Pythagoras' theorem, is that right? See, this thing that I'm telling you is related to Pythagoras' theorem, because Pythagoras' theorem in dimension 2 is that. In dimension 3 is that. But there's a Pythagoras' theorem in dimension infinity. I don't know if you've seen that. Maybe you haven't. That's okay. That's okay. Because that basically says that if I want to understand the amount of energy in a vibrating string, I look at the frequencies and I add the amplitude of the frequencies squared, and it gives me the same number. That's Pythagoras' theorem in infinite dimensions. And it's the one that is the foundation for the MP3 technology. The MP3 technology, in fact, uses that. But this is related to one-dimensional strings. What if we want to do music? That works very well, except for the drum. The drum will not be sines, there will be Bessel functions. I don't know if you've heard them. Bessel functions? No, you never, but you've seen them. If you take a drop and you drop it on still water, a drop of water into still water, you see that there's a little ripple. Have you seen the ripples? Well, if not, I'm sure on YouTube you can find the ripple. Yes? The ripple has what shape? Can you do it with your finger? It's circular, and it's like that, and then like that, right? That's a Bessel function. You see Bessel functions in two-dimensional surfaces. And that's how drums vibrate. But Bessel functions are not like sine functions, they're very different. Sine functions have this nice periodicity. The nodes occur at exactly the same distance, and Bessel functions, no, they're like that, and then they're closer. Okay? You can still approximate them, but they're worse approximated, so you have more noise. So that's good for music. Okay, so it's still good for drums, but what are you going to do now? Images. How does image compression work? Can I use sines and cosines for images? Images have rough edges, right? How can I compress the edge of that table against the black background? Or how can I compress my face in this video that Zoom is or was submitting in real time? Just what Zoom is doing, what all of these encoders, decoders are doing is exactly the same as we just described. But much more complicated because now I don't have sines. But I have other things, and these are some of the traditional objects which are used to replace sines. For example, that one is for JPEGs. The way you take a picture and you split it is with something like that, because pictures are like that. Your shirt is mostly blue, and then it stops, and then it's your skin tone. Then it stops, and it's the chair behind you. That's what I'm seeing. So with the superposition of these things, I can get a very good compressed version of what I see looking at you. And this translates into video, and then that's how we can do Zoom calls in real time. Because they are efficient. If they were inefficient, forget it. The delay will be like, whoo, right? Even recording will be very low quality, or you need huge tapes to record stuff. And everything that is data driven is like this. Everything. Face recognition, when your eyes sensor data, so like that. And this is what feature engineering is about. So at this point, this will connect very well with the course I will teach later on machine learning and data science. But I feel like I need to stop. This is enough, I think, to get an understanding of how the data around us can be understood, can be used. You can create the music industry, you can create the video industry, you can create the financial industry. And data, if data is the driver of all of that, I think we get a sense now of how we can use data in an efficient way. Because the problem with data, we have too much of it. We need to compress it. We need to understand how so much data can give us the pieces of information we need, which is very simple. Yes, give the loan. No, don't give the loan. That's it. All of that data is turned into a decision which is zeros and ones. And that is really what this world is about. And that's what I will be teaching in my course in data science. But today I just wanted to make the connection and how math is always there. So the better you're at math, the easier time you will have coming up with all of these inventions. Good. All right. So I don't know if I have more slides. Yeah, now I talk about regressions. I don't feel like I want to talk about that. I think I am very happy